So let's say we take 0 and we map it to 5 copies of 0, and you take 1 and you map it to 5 copies of 1. So suppose you have what's called a binary symmetric channel. So, so 0 is going to go to 0 with probability 0.9, but maybe it goes to 1 with, some small probability 0.1. And 1 goes to 1 with probability 0.9, and it goes to 0 with probability 0.1. So this is a 90% accurate channel. And it's binary because there's 2 inputs and 2 outputs, and it's symmetric because it does the same thing to a 1 as to a 0. And Shannon gave this theory of, started the theory of information in 1948. And before Shannon, everyone had the vague idea that essentially the best thing you could do was repeat bits. So if we repeat it 3 times, goes to 0, 0, 0. Well, the answer, probability of error, is equal to 0.1 cubed plus 3 times 0.9 times 0.1 squared, which is 0.028. 0.028. So that's better than 0.1, which is not encoding it at all, but maybe it's still not that good. And 0 goes to 0 to the 5th. You get the error down to 0.0086. 0 goes to 0 to the 7th. It gets down further, 0.0027 and 0.0009. 0 goes to 0 to the 9th. So you see, you can drive your error rate down to 0, but at the cost of making your input longer and longer and longer. So everyone had the vague idea that something like this was the best possible thing you could do, and to get the error rate down to 0, or close to 0, you had to use longer and longer inputs. And Shannon showed this was not true. He showed that there was something called the capacity of a channel, and as long as you're trying to send less information than the capacity, you can correct it arbitrarily well, and as long as you're sending more information than the capacity, you can't do, you're stuck with a high probability of error. So for the binary symmetric channel with error probability 0.1, the capacity is 0.531 bits per, I guess, channel use. So what you can do is you can take your message of length n, m, and encode it into 2m, and get very low probability of error. So instead of 0.028 rate of bit error, you could drive this down to 1 in a million probability of error, or 1 in a trillion, or 1, as low as you want. So this is, so the penalty you pay for using this is you need to use block encoding, which means you need to take 10,000 bits of your message and encode them in 20,000 bits and send them over. Then take another 10,000 bits of your message, encode them in 20,000 bits, and send them over the channel. So it's not going to work for very short messages. And the encoding schemes are much more complicated than this. So I guess, is it 2 years after Shannon's paper, Hamming came out with the first error-correcting code that's better than this. Actually, Shannon, I guess implicitly in his paper, he used error-correcting codes, but they were not, he basically showed they existed. He didn't give any good examples of them.